Hi and welcome everyone. Lag and immobility while trying to learn what the highest mountains on Mars are. The exercises are just for me, so if you follow along with the exercises, it is at your own risk. So here's a quite long explanation on what areoids are, or what the areoid is of Mars, because the mountains here are listed by the height what I have on Mars after the areoid. And I'm going to read and try to explain this explanation what the areoid of Mars is. So first, for beginning, very short, what these mountains are. Olympus, 27 kilometers, about this areoid. Explanation I'm going to read and explain in a moment. I try to. Arcia, 20 kilometers. S. Creus, 18 kilometers. Pavonis, 14 kilometers. Elysium, 14 kilometers. Pharsis, 9 kilometers. And Ceronius, 8 kilometers. Height above areoid. And the areoid is the geoid of Mars. So there is a geoid on Earth, and the same thing just on Mars is called areoid. On Earth it's called geoid, on Mars areoid. And the geoid is where the ocean has its surface. So the ocean, the seas and all the water, where the surface of it is. We don't regard storms or wind or tides, which maybe put the level of the surface a bit somewhere else, but just say the geoid is where the ocean has its surface. And also where this surface of water would be over land. So the geoid is also where it would be inside a mountain or on land. So it does not just end where the water ends from the ocean, but you also have calculated it further where this geoid line, where this water would be if there would be water on land, which would be underground oftentimes. At the geoid, the gravity is everywhere the same. So the geoid, at this point where we said where the geoid is, there's always the same gravity. Whether we have a geoid point over Europe or over North America or somewhere else, there's the same gravity at all these places at this height. So maybe the geoid is here, and the meter further where it is here on another height, but there's the same gravity. So there's the same gravity here, so the geoid could be here and goes to here, and there's the same gravity here as here from the Earth. For some reasons, we're going further. The water is pulled at all parts of the geoid with the same force to the ground. So the water could be here and could be here, but at both these points, these geoid points, the water is pulled with the same gravitational force to the ground, or gravity force to the ground. Now a bit more to gravity. Things can have the same size, but a different mass, and the mass makes how much gravity there is. So a large object with a lot of mass, and the mass is an important thing, not how large it is, has a gravitation. And this gravitation pulls things to it. The Earth is a very, not only large, but also something with a great mass. And the Earth pulls us very strong to it. So we are very strongly pulled to the Earth by gravity. And now here, things can have the same size, but different mass. 1 cubic meter gold has a density of 19,320 kilograms. 1 cubic meter is 1 meter times 1 meter, so something like this of gold, a block of 1 times 1 meter gold, has a density of 19 tons. So a gold block with that size would weigh 19,000 tons here on Earth. It would weigh something else somewhere else. This is something else. It weighs on Earth 19 tons, and the density is 19,000 tons. On Moon it would weigh only I think 6. It would weigh less. But weigh is something else than mass. On Earth, it is the same, I think. So on Earth, a cubic meter gold weighs 19 tons. But for us, important is it has a density of 19,000 tons. So a very big gravity compared to coal. 1 cubic meter coal has a density of only a little more than a ton. So this size of coal weighs 1 ton, and this size of gold 19 tons. So a piece of coal can hold good in hand, a sack of coal, but gold bar is very, very heavy, 20 times more heavy than coal. So gold is way more heavier than coal and has a greater mass and therefore a greater gravitation. So 1 cubic meter of gold pulls way more to it than 1 cubic meter of coal, even though they have the same size. Now a little imagination scenery. Two mountains with the same size are standing vis-a-vis and with a lake in the middle. So we have two mountains, they have the same height, the same circumference, all the same, they look the same, and in the middle is a lake, but one of these mountains has very much gold inside, and the other one a lot of coal. And now because this one mountain has gold inside, even though they have the same size, it has a greater gravitational force, because this one mountain with the gold inside has more mass, because gold has more mass than coal. And now this mountain with gold inside pulls the water from the lake to it. So if the two mountains are standing like this, the water in the sea is not even leveled, but a bit shifted to a gold mountain. Gold mountain pulls with the gravity, because it has more mass, because it has more gold, the water to it. And now the water is not even, but like this, like a tide, like with the moon. The water is pulled towards the gold mountain. The gold mountain has a higher gravity than the coal mountain. The water in the lake will be pulled a bit more to the gold mountain. The common used sea level would not incalculate this slightly leaning of the water to the gold mountain. It's very little, but it would be there. And the sea level would just say sea level is like this. It would not know that there is gold inside the mountain and pulls the water towards that mountain. And the geoid calculates that in. The geoid is hypothetically calculated further, not only where the surface of the water is, under regardless of the gravitation of the gold mountain pulling the water closer to it, but it also looks where it would be inside the mountain. So the geoid does not only know that the water is not like this, but like this, but also looks where would be the water if there would be water inside the mountain. And this is important now for the areoid on Mars, because there is no water at all. There are no oceans. There are no oceans on Mars. But the geoid works even where no water is, or no oceans in the case of Mars. The center of the mass of Mars was first calculated, so how we got to the areoid is not explained. We looked at where the center of Mars is. Mars is the whole thing, and it could be, in a hypothetical example, that the whole left side would be full of gold and the other one full of coal. And now the center of the mass of Mars would be not in the center in the dimensional sphere, but more to the gold. It would, in a way, fall to its side, however that would be explained in space. So first we looked, where is this center of Mars? Not of Mars, of the Mars planets, but of Mars. So we looked at it, and then the MGS orbited around Mars, a satellite, and measured the distance to the ground. So we know where the center of the mass of Mars is, and we had a satellite, the MGS, orbiting around the planet Mars, and looking how much the distance is to the ground. And with all the data, we calculated the areoid. Now a similar story. But first, why we called it areoid? Because the Greek name of war is Ares. So a couple of thousand years ago, the Greek called it Ares, their god of war. And the Romans had also a god of war, and that was called Mars. And the Mars, the planet itself, is called after the Roman god Mars. But the Greek also had a god of war, and that one was called Ars. So this thing is called Ars, Areoid after Ars, and Oid, which is in Greek like. So that's why it's called Ars. Now the other story. In 2002, two identical satellites orbited one after the other around Earth. So in 2002 we had two satellites orbiting around Earth close beside each other, behind each other. And if there was a gravitational anomaly somewhere down in the Earth, the different pulling force would pull a bit at the first satellite. So we're traveling here, and then the other gravitation, somewhere from the Earth, pulls at the first one. And this changed the distance to the other one. First they are at equal position, and now they travel, and there's something differently pulling on the first one, because it's now over a place on the Earth, the gravitation is different, and now the distance of the two has changed. In an extreme case, so they were like that, and when it was taken down, now the distance has massively changed, and if we calculate all around this, we knew that there were a difference in the gravitational field of Earth. From the difference of the distance of these two satellites. And now another story to it. In the Indian Ocean. So here's North America, there's Europe, there's Africa, here's Asia, and there's India. The Indian Ocean is here, south-like of India. So in this Indian Ocean, there is a 3,000 kilometers times 3,000 kilometers. So a very, very large place. It has around the size of India itself. It's not directly 3,000 times 3,000 kilometers, but we take it. So 3,000 times 3,000 kilometers. Large gravity anomaly. At this place, the ocean water is 106 meters, lower than it should be. At this place, there is less gravity. For some reason, there is less gravity at this large place in the Indian Ocean. And the water is pulled by greater gravitational forces to the outside. So there's, for some reason, less gravity here, but there's much gravity here and here and here, and the water is pulled away to the greater forces. And through that, there's less water, and the sea level now says the water is in the oceans at sea level, and says the water should be up here, 106 meters higher. But the gravity actually is not strong enough, the other gravitational forces are higher, pull the water away, and the water level is actually 106 meters below sea level. At a very large space, 3,000 kilometers times 3,000 kilometers, the water in the middle of the ocean is 100 meters lower than the sea level says it should be. Now the last exercise. And the geoid. Now, so the geoid was calculated and is still calculated and made more accurately. Now that at some places the gravitational force is lower and at others higher, and knows that at this place the sea level is lower. The sea level but the actual level of the water is lower. The actual level of the actual water sea is lower. The sea level says it's still up here, but it's actually 100 meters lower. And this is the area, just the same thing for Mars. There the water would be on Mars, if there would be oceans. And after that calculated, Olympus is 27 kilometers above the Areoid. So Olympus would be around 27 kilometers above sea level, but sea level is not exactly the geoid, but over the Areoid. And the next one would be Asia, with 20 kilometers above the Areoid, named after Ares, the Greek god of war, Ares. Areoid on Earth, geoid. And Asclepius with 18 kilometers above the Areoid, Pavonis with 14 kilometers, Elysium 14 kilometers, Phasis 9 kilometers, and Cheronius 8 kilometers above the Areoid, named after Ares. But it's Areoid on Mars and Geoid on Earth. I thank you very much for your attention, and until next time.